the next part of this lesson is the DC load line analysis. Okay, actually we have discussed this topic in our previous class. So we'll do the explanation again before we do some examples. Okay, how to draw the DC load line. The DC load line is when you do the DC load line, the prerequisite is you need to have the output characteristic of the BJT. So when you have the output characteristic, this is important for you to have the output characteristic in order to solve the problem, the DC analysis. Okay, the load line of the BJT is generated from the KVL of collector emitter current path. So we have here, this is for example here for the BJT. If I draw the NPN BJT here, so this is collector, this is base, and this is emitter. So the current at the collector is collector current, IC. The current at emitter is emitter current, IE. And voltage across the collector and emitter terminal is VCE. Okay, so if we do the KVL along the collector and emitter current path, so we will capture the IC, VCE, and IE. Okay, so the load line should have the IC and VCE. Okay. Now we need to apply an approximation that IE is equal to IC. IE is equal to IC. So IE will be approximated to the IC. So why we can do this? Because we know that the base current is very small. IE is equal to, from the KCL, IE is equal to IC plus IB. But now the IB is very small, so the IE can be equal to IC. We do the approximation. So when we do the approximation, the KVL equation will only have the VCE and IC as the parameters. Okay, so once you have this KVL, so you can plot the load line. So the load line is a linear equation. So to draw the linear equation, only 2 points are needed. So we have the 2 points here. We have two conditions. The first condition is the point where the VCE is 0. So VCE is 0. This is the first condition. When VCE is 0, we have the maximum collector current. We call it saturation current. IC set. So this can be done by inserting the VCE equal to 0 into the KVL of the collector emitter. So and then the second point is when we consider the collector current is 0. So when collector current is 0, so this is the VCE is equal to cut-off voltage. So this is a cut-off. Okay, so once you have plot the load line, and then you should plot the load line at the same graph, with the output characteristic. So when you draw this load line, you can determine or you can identify the intersecting point between the load line and output characteristic of BJT, and the Q point is the intersecting point. Okay, in order to identify the intersecting point, you need to know the base current. You need the base current before you can determine the Q point. And then another thing that you need to remember that for the beta, usually if you do the DC load line, you can manually extract the beta extract the beta, and the beta can be directly calculated from the graph, ideally at the Q point. Okay, without further ado, we see the example here. Okay, this is a emitter stabilized by circuit, and at the right side is the output characteristic, collector current versus VCE. And then you see many lines here actually represent in many conditions, in many cases where the IB is different value. So this line is when the IB is equal to 0 microampere, and then this is when the IB is equal to 30 microampere. Okay, so let's see the question here. Draw the load line on the characteristic of the BJT. Okay, draw the load line. Okay, how to draw the load line? The load line is from the KVL collector emitter. So the KVL collector emitter is in this direction. Okay, before we do that, we need to remember that we can remove this C1 and C2 because this is a DC analysis. Okay, so the KVL is minus 18 plus, so this is IC, this is IE. So IC times 2.2K, and then we have here between collector and emitter we have the VCE here plus VCE plus IE. This is 1.1 K, so it's equal to 0. So in the load line we will do the simplification. IE is almost equal to IC, so you got here this one is 18 plus IC 2.2K plus 1.1K plus VCE equal to 0, and this is 18 plus IC 3.3K plus VCE. Okay, so you got this equation. Okay, from this equation you can draw the load line. Okay, no need to rearrange this equation. You can use this one as long as you have the plotting point. So how you do the plotting point is let's say you put it like this. This is the VCE, and then this is IC. You have the one condition is when the VCE is 0. Okay, this is the first point. When the VCE is 0, okay, at this point the IC will be equal to, if VCE is 0, so IC equal to 18 over 3.3K. So calculate this one. 18 over 3.3K, 5.45. You have this one is 5.45 milliampere. So you have the first point is 5.45 milliampere. So the first point should be around this one. So this is the first point. Okay, and then the second point is when the IC is 0. When IC is 0, VCE is equal to 18. So you got this around here. This is the number 2 point. Okay. So now you can draw the straight line from these 2 points. Okay. So this is your load line. So this is the answer. for the first question. Okay, the next question. Okay, the next question is Q point at intersecting with the base current of 15 milliampere. Okay, so let's assume okay, you have this one. Okay, assume this one is your load line. So you have the IC saturation is between 5.45, and then you have this one is actually is 18. Okay, so let's just assume this is 18. So this is 18. Let's assume this is 18. So Q point intersecting of the load line with a base current of 15. Actually, this one is micro, because the base current is 15 microampere. So identify where is the 15 microampere. The load line is, the intersection is here. So now you can get the value. So roughly the ICQ is equal to 3.2 milliampere, and then the VCEQ is equal to, this is at the middle, so let's say this is 7.5 volt. Okay, in actual test or exam, if this type of question is given, so there will be a proper plot graph, so you can read the value more precisely. So this is the second answer. This is the final answer for the second question. So just identify the intersecting point once you know the base current. Okay, and then determine the beta at the Q point. Determine the beta at the Q point. So you know that the beta, the equation of beta is equal to IC over IB. Okay, from the analysis, we know that the IC is 3.2 milliampere. So 3.2 milli at the base current of 15 micro. So this is actually 3.2 milli over 0.015 milli. So this is equal to, beta is equal to 3.2 over 0.015. This is 213.3. So this is the value of the beta. Okay, and then the last one is using the beta for the network determined in the part C, calculate the required value of RB. So beta in the part, the second part, the previous class slide is 213.3. So you need to determine the RB. So recall back on the procedure for the DC analysis. Okay, this is the RB is actually is appear in the KVL of the base emitter. Appear in the base emitter. So what you can do is you can do the KVL here, and the KVL at base emitter. So the KVL is minus 18 plus the current at the base RB is IB. You have this one IB RB, and then the voltage drop at the base emitter is 0.7, and then the voltage drop at the RE is IE 1.1K equal to 0. Okay, so you may notice that the IB here, what is IB? IB is given as a 15 microampere or 0.015 milliampere. Okay, can put this one is IB. How about IE? What is IE? Okay, IE you can use the this beta plus 1 IB, or I can also use another solution, which is IE is equal to IB plus IC. So IB is 0.015 milli, and then IC is 3.2 milli. So you got here is 3.22 milliampere. Okay, so insert the value in the KVL. So you got this one is minus 18 plus 0.015 milli RB plus 0.7 plus 3.22, this one is milli, 1.1 K equal to 0. So you solve all this equation. So you get this one, this RB. So let's say we solve it term by term. This is minus 18. Okay, this is cannot be solved. This is 0.7. Okay, and then this one is 3.22 times 1.1. This is 3.54. So this is equal to 0. So we know this RB is equal to 18 minus 0.7 minus 3.54 is 13.76 over 0.015 milli, 0.015 milli. So here we get this one is 907.3 kilo ohm. So this is the answer for the RB.